And we are now recording. So again, I'll ask any questions, problems, issues. I heard none before. Before we get going here, let me just mention a few things. I'm kind of preaching to the choir here because y'all are pretty much up to date, I think, on just about everything. I can't say for certain because I have been getting papers in faster than I can grade them. So now my stack is up to here, even though I got some grading done. So this is fighting a losing battle, it seems like, but hopefully I'll get caught up some this weekend. But I have just 7 active students that I can tell in the class. There were 2 that never paid, so they got dropped, and it looks like 7 paid students, and 6 of you are pretty much on top of just about everything. Okay. One student hasn't been here in a couple of weeks now, getting close to 3 weeks now, 3 weeks I think it is, and I don't know what he's going to do. He hasn't turned in any tests, and so I don't know what's going on with that. There's a couple who haven't turned in test 3, I don't think yet, but they're not here. They may be in that stack. Okay. And test 4, is that the one I'm going to give you today? I think it is. Okay. So I will give you this today, and I'll encourage you try to have it completed by next week, because I'll be giving you I'm sorry. Okay, test 4 Tuesday. That was the chapter 12 16 test, right? Yeah, okay, that's the one I meant. Okay. I had forgotten to send it out Tuesday. I remember now. I said I would. I did. Okay, so it's out there. Try to have it in before next Thursday. So, because on Thursday we will, today, Tuesday, and Thursday, we'll get as far as we possibly can in 17, and then I'll be giving you the chapter 17 test on Thursday. Okay. We aren't going to get to chapters 18 and 19, so we're not going to get that test. If we had our full 10-week summer term, we would have gotten there. But they cut us short at 8.5 weeks, so not going to make it. Okay? But I think just about everything you need for your course, for your diagnostic medical sonography, hopefully I've covered. Anything I may have missed, feel free to always contact me and try to catch up, and I'll try to help you fill in any gaps that you have. But I guess you have the books, or at least access to a book, so please see if you can figure out based on what we've done so far. All right, with that in mind, any questions, issues, concerns? Yes, okay. Just the way you've been doing. It'll only be chapter 17. It will not be comprehensive. So it's just going to be another test just like we've done. And I'm glad you said that, because I meant this to say a little more about it. So here's the more I want to say about it. I'm going to give it to you Thursday evening. Sadly, that means you only have Friday, Saturday, and Sunday to get it done. You will not have a full week to do it, because if my understanding is right, and I may be wrong on this, but if my understanding is right, we have to have our grades in by noon on Monday. Okay, so that means I've got to have those tests. I'd love to have them on Friday. It'll be okay to have them on Saturday. Sunday's pushing it, but certainly I'll accept them. But if you don't get them in to me until Monday, there's a good chance you're going to get it incomplete, because I will not have time on Monday to grade a bunch of papers, get the grades on Blackboard, calculate those, and get the grades by noon on Monday. So I may have to just give I's, then as things come in, grade them, and then change the I's to letter grades. Okay, so please, if you can, get them to me preferably Friday. Next preference is Saturday, and please get them to me by sometime on Sunday so I can try to get them graded, and so we can wrap up the term that way. All right, any questions on that? Sorry, It's going to be pressed, but I'm going to try to make the test pretty short and sweet. Hopefully you can do it. I won't know how to do the test until the end of the class on Friday. I'll have it ready, and then anything we don't get to cover in 17, I'll say, okay, these questions are optional, because I can't tell how far we're going to get it to go. All right, any questions on that then? Good question, by the way. All right, we were on page 446, chapter 16, wave motion and sound. We're right at the last example in the chapter, and we'll do that. Right above that, it says try this activity, swing set physics. That basically is a pendulum. So exactly what we're talking about there. Swing offers a good pendulum. Using a stopwatch, measure the period of the swing as it moves forward and backward. Make one complete sweep and vary the amplitude of the swing, meaning you take it up a notch if you can. The mass of the person sitting on it, you'll find out, doesn't matter at all. The length, okay, oh, I'm sorry, the amplitude of the swing is how hard you push, how high they come. That doesn't matter, okay? All that matters is the length of the swing's chain. Now, if you can change that, you can do it. That's not necessary, but if you want to test this out, you can try it. Okay, now let's move on to example 1 in this problem's in set 16.6 and example 1, the only one and only example. Okay, find the length, and they've been calling that little l, that's the unknown here. Find the length of a pendulum with a period. So the period, the symbol for that is capital T, and the period of 1.50 seconds. Remember, capital T, little t usually stands for time. Capital T is a time, it's a specific time, and that's the period of a wave or of a pendulum or of whatever. Okay, now since okay, and by the way, they said find the length in centimeters, so I probably should put that there. Okay, of a pendulum with a period of 1.50 seconds. Okay, which system are we in if we're looking for the length in centimeters? And it's almost a trick question. Anyone have a guess? It's definitely metric and not US customary, but it isn't SI. So we have two options here. Oh, let's go on and put down the formula that deals with this. And here's the formula that deals with it on the previous page. T, that's the period, is equal to 2 pi. Those are both just numbers. 2 is a integer. Pi is an irrational number, okay? Times the square root of L, where L is the length, and G, where G, what in the world is G? Anyone want to hazard a guess? What in the world is G? Okay, it's the acceleration due to gravity. And since we're in centimeters, another sort of trick question. I'll put it this way. You don't want to use 32.2 feet per second squared. That's US customary. So what's the other measure for gravity? It's on the previous page if you need it. Anybody? They list it as 9.80 meters per second squared. Now, does anything seem to be inconsistent with this problem as stated so far? Hint, the length is in centimeters, the acceleration due to gravity is in meters. There's the issue. Goodness gracious. Every class today, my phone has started reading. I don't know who it is, but I really don't care right now because I'm in class. I'll try to find out who these people are after work today. And if you hear that buzzing, that's what it is. And it just keeps buzzing. Okay. Now, so we have one of two choices. We can either use the G in meters per second squared, calculate our L, and then change it to centimeters. That's a perfectly legitimate way. Or we could change the 9.80 meters per second squared into ever how many centimeters per second squared that is. That's a perfectly good way. So I'll let you decide which way would you like to do it. Calculate using meters and then change your answer to centimeters, or change the G to centimeters and then do your calculations and you'll get L in centimeters. You choose. Which way would you like to go? And if you're trying to answer now, you're all on mute. So whoever's trying to answer, unmute yourself so I can hear you. And Mercy, your box is lit. I don't know if you're trying to say something or not. Or is that because you asked the last question? Okay, someone give me an answer. Calculate in meters and change to centimeters, or change the meters in G to centimeters and calculate in centimeters. One or the other. Someone answer. Okay. Okay. Change the, is that what you said? Change the meter to centimeters? Okay. All right, let's do that. All right, so here we have G in meters per second square. We're going to multiply that, if my pen would agree with me, multiply that by blank blank, this is how we do our conversions, to equal blank centimeters per second squared. So we don't have to do a thing with the centimeters, with the seconds. They're already in the unit we want. However, we need to get the meters over here changed to centimeters over here. So one of those units is going on top and one's going on the bottom. Always put the units in their place. The two blanks, the first blank is for numbers, second blank for units. Always put the units in the place first. What unit goes where? One goes on top, one goes on bottom. There's your multiplication there. There's your equal there. Meters go one place, centimeters go the other place. What goes where? Anybody? All of you are muted. What goes where? Make a guess. I'm drowning here. I need help. Anybody? Come on. Centimeter goes either on top or bottom. Meters go on the other place, bottom or top. Who goes where? Why is, okay. Anybody? This pen is just nuts. One goes one place, one goes the other. Someone help me. Y'all are not saying a word. Okay, I'll go on and do it. We can't waste any time. Meters goes on the bottom, so it will cancel out with that meter. That means centimeter goes on top, and that's exactly where it is here. So that makes sense. Now we have to figure out how many centimeters are in a meter or how many meters in a centimeter. Can anyone answer that one?
100.
Which one? Say again? 100 centimeters is in 1 meter. You're absolutely right. And what that does when you multiply here is move the decimal 2 places because you have the 2 zeros there. Okay? So that means you got 980, and that is a significant zero, centimeters per second square. It's just another way to express the acceleration due to gravity. Now, we've got work to do here. And again, you have a choice. You can chug and plug or plug and chug. In other words, you can plug in the numbers as you know them, and then you have to rearrange the order. Or, usually it's easier to rearrange the letters to get the letters like you want, and then plug in the numbers. Which way do you want to do? Plug first or rearrange first? I agree with you there. So what we're trying to do, because what we're looking for is the length, we're trying to isolate the length. So the first thing we're going to do is divide everything on both sides by 2 pi to isolate the L. Okay? Now what that does for us, it wipes out the 2 pi here and here. Okay? So now, I'm going to reverse sides at the same time too. We've got the square root of L over G is equal to T, the period, over 2 pi. Now again, our goal here is to isolate the L. What do we have to do before we can isolate that L? What's in the way? The square root symbol. And how do we undo a square root? You square both sides. Okay, so if you square this side, that will lose your square root, and you square this side as well. Okay, so now what we'll have with the square undoing the square root, okay, what we'll have is L over G is equal to T squared, the period squared, yuck! Okay, it disappeared, that's good. The period squared over 4, 2 squared is 4, and pi squared is pi squared. Okay? Now, we've got one more step to isolate the L. And what's that? Yeah, and how you do that is multiply both sides by G. Okay? So you got rid of your G's on this side, and now we have L is equal to T squared times G divided by 4 pi squared. Now, your period was 1.50, so that's 1.50. Would you quit this? Okay. Okay. 1.50 seconds squared. You got to square the number and square the unit, divided by 4 pi squared. Now neither one of those has any units, so it's just 4 pi squared, times your new G, which is 980, and that's in centimeters per second squared. Now I'll tell you what's going to happen. The second squareds are going to go away. Okay? So we pull out our handy dandy calculators. Mine's my telephone, that if it'll just not ring while I'm working on it. Okay? So I was on the phone at least an hour this afternoon advising students, so got to get my calculator back up. Oh, wait, here comes somebody. I can't tell who it is. Manessa. Excellent. Okay. So Manessa's here. Okay, finally the first part of the alphabet has somebody to hold it down. Okay. Welcome, Manessa. Now, by the way, Probably will say this every time someone new comes into the class. Just a little bit of a refresher here. I'm preaching to the choir in most of this now. Test 1, all of you and 2 others have turned in test 1. Test 2, all of you and 2 others have turned in test 2. Test 3, all of you have turned in test 3. Okay? I did give you your test 4 last time. Y'all reminded me. I know I said I would, and I couldn't remember if I got it done or not, but I sent you your test 4. We're doing the last problem in that chapter right now. So as soon as we finish this problem, I'll make the homework assignments, then we'll be moving on to chapter 17. So I would love for you to have the chapter 16 test 4, completed and turned in to me as soon as you can. Preferably, well, if you have it almost finished, I don't know if you're that far along, I doubt it, and you could turn it in this evening, that would be wonderful. But if not, get it to me sometime tomorrow, sometime Saturday, or sometime Sunday. Even sometime Monday would be okay. We're got to go out of town this weekend, and where we're going to be has terrible internet service. It's very slow and very unreliable. So the odds are I'm not going to be able to print, and we're not going to be at a place where there's a printer available. So therefore, I'm not going to be able to print anything this weekend. So if you get it into me tonight, I can get it printed tonight, possibly, and then maybe work on grading it some this weekend. This weekend is awfully full. We got work to do over at the farm in Georgia, and so I'm not going to have a lot of time, but I'm going to take all those papers I showed you earlier, try to get as many graded as possible. Probably not going to be too successful, but I'll get as many done as possible. We come back early Monday morning. We're going to leave very, very early Monday morning. Hopefully be back 10:30, something like that. But I have a class starting at 11:30 and then another one at 2:30. So I'm going to have very little time on Monday to do much more than catch up with emails and print more stuff that's coming in this weekend. So that means starting Monday evening, I'm still going to be printing stuff, but I'm going to be grading like crazy. So things are behind on Blackboard, so don't expect to see. I've got, like I said, all those things graded. I don't know if it's all out on Blackboard yet, but get me your stuff as soon as you can. Because today we're going to start in chapter 17 very shortly, and then we'll get as far as we can today, as far as we can Tuesday, and get as far as we can on Thursday. At the end of class on Thursday, I will give you the test for chapter 17. I'll let you know which questions you need to answer, which ones will be optional, because I won't know beforehand how far we're going to get, so I'll probably put a few extra questions on there just in case we don't get as far. Well, if we get further than I think we will. So, and then once I give you that Thursday evening, sorry it's very short time notice, please get it back to me Friday if possible, Saturday if you can't get it to me on Friday, and try to get it to me no later than Sunday, because I have to have grades in Monday at noon, and I can't be receiving new tests on Monday and hope to get them graded, grades averaged, and grades put out there before noon on Monday. So please try to get me everything you can that you have in your hands now by next Monday, this coming Monday, and then everything what I give you on, well, you can take another day or two for that last test, but once I give you that last test, you don't have much time. Please get it to me just as soon as possible. If you don't have it to me before Monday morning, you're probably going to get an incomplete, but get it to me as soon as possible, and I'll change the incomplete to a letter grade. So please, just wanted to make sure everybody heard that. Okay, so let's get back to this problem. We're doing example 1 on page 446 in section 16.6, and how you, the class, chose to do it because we had our length. Can't write with that, need to write with this. The length that we had, they were asking for centimeters. The period was given in seconds, okay, and the but gravity was given in meters per second squared. So y'all chose to change the meters per second squared to centimeters per second squared, which became 980 centimeters per second squared would be the acceleration due to gravity. That's what we're about to plug into our calculators, and that's what I had my phone in hand before Manasseh came in. So let me get it back again. It already timed out on me. There's my calculator. So what we have is 1.5 squared, that's times 1.5. You don't need the 2 zeros here, but you could put them if you wanted to. And then we're going to multiply that by 980, and then we're going to divide that first by 4, and then we're going to divide by, and because I have to turn my calculator sideways to get a pi, we're dividing by pi, and just to keep from doing this, okay, what I'll do is then divide by pi again. Okay, that's dividing by pi squared. Okay, and what that gives me, at least I get about 55.9 centimeters. No, okay, let's look at the units. Yeah, the length would be centimeters because the second squared canceled out, and that gave me 55.9 centimeters. How did the book do? I haven't looked at it yet. This is 55.9 centimeters. How'd the book do? 55.9 centimeters. Good for them. Now the book chose to do it the other way. They left everything in terms of meters. So then at the end, when they got 0.559 meters, they had to turn around and convert that to centimeters. Either way, 6 of one, half dozen of the other, they both work. Any questions on that? All right. Now I did my division one way. If you want to do it using parentheses, you could do that. If you want to write down the answers every step and do that, whichever. That finishes section 16.6. It finishes all in 16. Here are the problems that you might find useful to help do your test in for the test 4, which is chapter 16. Any of the odds 1 through 13. And then we have the glossary, lots of terms in this chapter. So I would read through those. This is an important chapter for you because it's wave motion and sound. Formulas are given. Those are pretty important too. You probably won't need the pendulum period, but if you do, there it is. Review questions are mostly conceptual, but the review problems, they're far more like what you're going to see on the test. So any of the odds 1 through 17 there would be okay if you need a few more to work on. I've already pointed out to you the Galloping Gertie is what someone nicknamed it, the Tacoma Narrows Bridge, and this was back in the I don't know what year it was, 1940. Okay, this bridge, beautiful, fantastic looking bridge, and it fell apart. It tore itself apart because of resonance. The resonance of the bridge, the natural frequency of the bridge was right about the same as the natural frequency of the wind in the area, and when they had sustained winds for long enough, the bridge started resonating with the wind, just literally started moving on its own just because of resonance, and tore itself apart, ripped itself apart. There were cars on the bridge at the time. Some of them wound up in the bay and Puget Sound, and some of the people died. I don't know the whole details on it, but anyway, that's there. There's many other things you can look at for applied concepts. They list several here. I don't know if this has ever happened to you, but I've had it happen to me before. It's been years, but it has happened, that if a tire wasn't quite in balance, okay, they do much better job of balancing tires today than they used to, but if it wasn't quite in balance, then there would be some frequency at which it started shaking, okay? And it was really bad if that's around your normal driving speed, like 60 miles per hour. Then you'd be shaking like this. You'd either have to drive faster and risk getting a ticket, or drive slower and risk people honking their horns at you. But if you drove at that speed where it had the resonating frequency, you felt like your car was going to fall apart. And it may have been that it would. Okay, so there are other examples here. The one on a jet engine technician is that same type of a deal. Okay, let's move on to chapter 17, basic electricity. So I'm going to end the whiteboard for now and go to chapter 17 here. All right, and we'll go from current slide. If I can get this set up. And here we go. Basic electricity. Now, I think I mentioned to you before, the only sections you're responsible for are sections 3, 4, 5, 7. Well, we got to do 6 because 7, 8, and 9 depend on 6. So 3, 4, 5, 7, 8, 9. But before we get too far, it's pretty important that you understand electric charges. So let's just quickly do what they show us here. Okay, I'm not going to go into great detail here, but I guess I will type some of this. So let me go back to the whiteboard, and we need to hurry, but I want to make sure you understand this. Anyone need that last problem any longer? Okay, so let me type what some of these definitions are. This is pretty basic fundamental stuff. Well, it didn't get me my text. Now, I don't know why it won't give me the text. Okay, can anyone remember what I've done before? Maybe, let me try this. Go out of screen sharing. Well, let's just go to another whiteboard. Okay, now let's see if it'll give me the text. No, it won't. So let me go back to chapter 17. And then go back to the whiteboard and see if it'll let me do the text. No, it won't. Okay, it won't let me do this. So I'm not going to type it in. I'll just read it to you. If you got your books, it's here. So let me go back to chapter 17. I don't know why that's not working. It gets aggravating. Okay. Now, an atom is the smallest particle that an element will ever exist as. Okay, it means indivisible. You can't split it into anything smaller. That's an atom. But atoms are made up of smaller pieces. But these smaller pieces won't be that stuff that you're talking about. Like an atom of iron, that's as small as you can get. If you split those up into protons, neutrons, and you have a mess. You don't have iron anymore. Okay? So, an atom has two major parts. There's the center part that's called the nucleus. That's incredibly tiny in volume, but incredibly massive in mass. Okay, it's got it, all the mass basically of that atom is in that tiny little nucleus. Most of the volume of that atom is occupied by these tiny little electrons. I mean, when I say tiny, really tiny, floating around that nucleus. Okay, the electrons have almost no mass whatsoever. Okay, they're close to 1/10,000th the mass of either of the particles that could live in a nucleus. So they're incredibly small in mass, but they take up most of the volume. They're just a cloud. It's sort of like the nucleus is like a solid and the electrons are like gas particles. Okay, only they're even further apart than that. So what are the components that make up the nucleus? There are two components. You either have protons, which are positively charged, P, positive protons, or neutrons, which are neutral charged, zero charge, no charge in a neutron. The neutrons and protons are almost the same size. If anything, the neutrons are slightly more massive than a proton, but not much. Electrons, almost no mass at all. They have some, but not very much, but they fly around. The electrons, however, have a negative charge. Even though they have almost no mass compared to the proton, which is really massive, but proton has one positive charge, that tiny, tiny little electron has one negative charge. So it has just as much charge, only the opposite side, as a proton. The neutron, on the other hand, even though it's very massive, has no charge at all. Now, I think we can blame Benjamin Franklin as being the first one to refer to charges either being positive or negative. And so I assume he just arbitrarily chose the electrons being negative and the protons being positive. Okay? Except I don't think he called them that. He just said positive and negative charges. Okay? And the study of that is then called electrostatics. And then you deal with static electricity. We're not going to get into that. This figure here shows a normal atom. Kind of, it shows a normal atom. Not quite. Okay? This atom has no neutrons in it. They're only showing the positive protons living in the nucleus. Now these sizes are way, if that's representing masses, they should be way bigger than these electrons. Okay? Because electrons, they should be more than, or on the neighborhood of 10,000 times the size of this. Well, of course they're not going to do it. You wouldn't be able to see the electrons, and the protons would take up too much room. But this would be, if it only has 3 protons, that would be, if this were real, a lithium atom. But lithium atoms always have neutrons as well, typically 3 neutrons. But since the neutrons have no charge, they're not showing them here. Now, the other thing that's a little faulty or phony about this picture, the 2 inner electrons should be closer to the nucleus, and then 1 outer electron way, way away. I can't tell which is inner or outer. They all look the same distance. So this is just a qualitative picture. It's not quantitative at all. The sizes aren't right. The distances aren't right. Now, if that lithium were to lose that outer electron that's way away from the nucleus, and it does, it loses it and it goes off somewhere else. Now that becomes an atom with a positive charge, which we actually call an ion, I-O-N. A charged atom is called an ion. This one would be a +1 charge. Lithium does exist. In fact, it exists a lot in nature as a +1 charge. It's real easy to lose that outer electron. This never happens, but just for sake of illustration, they've shown it happening, that it picked up an extra electron. Lithium never picks up an extra electron. But if it would, then this would be a negative lithium ion. They don't exist in nature, so don't even imagine they would. And electrons certainly wouldn't be equidistant like these. So this is just showing what would happen if you did pick up an extra charge. Okay? So I think that's all you really need to know here. They go into electroscopes. You don't need that for what you need. So let's move on past that, past the electroscope. Of all the times when they have a lot of slides, it's the things we don't need. I don't know if you've ever seen a Van de Graaff machine, but this is charged. Oh, here comes Jalen. Well, Jalen was already here. He must have got kicked out or had to go out, and he just came back. But I already had him present. Yeah. Okay? That's all right. No problem. Glad you're back. But if you've ever seen this, these kids, they don't notice it, but they're getting charges, probably electrons charged, and those electrons go to their extremities, which are your hair. And then the hair is negatively charged, and these tend to move as far apart as they can. And that's why these kids, their hair is standing up. They didn't come in looking like that. They did just because of that. And here's the reason for that. Because like charges repel each other, unlike charges attract each other. And those are extra electrons, and electrons are all the same charge, negative, so they push the hairs further and further apart. If they were positive charges, it would do the same thing because positive charge. But if they were some positive, some negative, wouldn't bother at all. Okay. Now don't tell me that's the only slide in the chapter. No, here we go. All right. This is way beyond where we're going next. So if we'll turn on over to 17.3, that's on page 455. We'll go back to the white page. Okay, we've got 4 students here, that's right. Back to the whiteboard. And here we're talking about Coulomb's law. Okay? Now remember I said before, I used the term real quickly, electrostatics. And basically Coulomb's law describes what's going on with electrostatics. And by the way, time out for just a moment. This I found so interesting. Robert Van de Graaff, that machine we saw with the kids with the hair standing up, he created these Van de Graaff generators. They have a little blurb here about Robert Van de Graaff on page 455. Here I found this so interesting. I didn't know this before I read this book. He was a physicist born, guess where? Tuscaloosa, Alabama. I never knew that. Okay? I don't know if he went to school here or if he went off to a bigger school somewhere else, a more prestigious school. This was back in 1900s, the early 1900s. So I don't know, but he was born in Tuscaloosa. I didn't know that. All right, let's go back to Coulomb's law. Now, the charge on a proton, okay, the charge on a proton, remember a proton is a positive charge. So, and the charge on that, there's my pen. Okay, the charge on a proton, I usually represent this way. P plus, meaning it's a positive charge. However, the amount of charge on that is the same as the amount of charge on an electron, which is called E minus, because that's a negative charge. But this book and a lot of books will use E to represent that smallest unit of charge that can ever exist in nature. And that's the charge on an electron or proton. So therefore, they'll call that E, and then they'll call it E plus for a proton and E minus for an electron. It's one electronic charge. Even though with a plus, it's really talking about a proton, the amount of charge is the same. So that's why they say that. It's a rather strange looking thing to say E plus because electrons are always negative, but that's what it means. Okay, now that's a microscopic quantity. An electron is an incredibly tiny piece of matter. They've never even been able to determine its volume. It's too small to determine. They do know its charge, but they have never been able to measure its volume. You can measure the volume of a proton. They're considerably bigger, but not an electron. You can measure the mass of an electron. Barely, but you can. Protons, much easier to measure. They're still hard, but much easier than protons. Now, on the macroscopic scale, the scale where we measure things, they want a lot bigger charge than an electron charge because that's so incredibly tiny. So the macroscopic charge is called 1 Coulomb. Okay, named after Charles Coulomb, so they capitalize it. Now it's a lot like degrees Celsius, but degrees Celsius will always have a degree symbol in front of it. A Coulomb, though, is just this. Okay. Now, the measurement of a unit of charge, 1 unit of charge, and whether it's E plus or E minus, so I'll do the plus down here, that would be 1.6, and it'll be positive because it's the positive, 1.60 times 10 to the minus 19 coulombs. A coulomb isn't that big a charge, but an electron charge, the charge of 1 electron, is so incredibly tiny. Now this would be of 1 proton because it's a positive charge. The only difference is if you were doing it for the electron here, then it would be a negative 1.60 times 10 to the minus 19. Okay? It's just that it's a negative charge, a proton is a positive charge. That's an incredibly small amount, and that's the smallest charge you'll ever find in nature. You can't get a fraction of an electron charge. Smallest you get. Okay? Now the other way to look at that, it takes, this is another way to express it, 6.25 times 10 to the 10 to the 18th power electrons to make 1 coulomb of charge. Okay? So in other words, that's an incredibly small amount, and that would be a negative 1 coulomb, by the way, too, because electrons are negative. But it's an incredible number. That would be 6, 250, 000, 000, 000, 000, 000, 000, 000. I don't even know what the name. 3 zeros would be 1,000, 6 would be 1,000,000, 9 would be 1,000,000,000, 12 would be a quadrillion, 15 would be a quintillion. I don't even know what you call 18 decimal places. It would be an incredibly large number of electrons to make just 1, and not just 1, 1.00. This is very precise. 1.00 coulombs of charge. Okay? Now, you can picture a 100-watt light bulb. Okay? That's how many, about the number of charges that would pass through a 100-watt light bulb in 1 second. So when you're talking about electrical charges and stuff, an electron is so incredibly tiny it takes quadrillions of them to light up a light bulb. Okay, so that's why we use coulombs, because that's a much more useful thing. Now, Coulomb made scientific study of the forces of attraction and repulsion between the various things that are charged, and in such they named the law that he discovered after him. And I wish I could type on the screen, but it's not giving me the opportunity to do so. It seems like I figured out something to do one time and it worked, but I can't figure out what that is again. I thought checking out and checking back in would do it, but it doesn't do it. So here's Coulomb's law. It's in your text. Hopefully you got it. The force between 2 point charges, Q1 and Q2, okay? The force between those 2 charges is directly proportional to, so I think I'll write it this way, because this actually is better than typing it. The force is directly proportional to the product of the charges, Q1 times Q2, but inversely proportional to the product of their magnitudes. We won't take the signs into account, just their magnitudes. Inversely proportional to the square of the distance between them. So we'll call that d squared. Now, to change the proportionality to a equal sign, you introduce a proportionality constant, K. And that's what we call it, KQ1, Q2 divided by, now the book uses, rather than D, they use R. Okay, the distance between them squared. Okay, that is Coulomb's law. Okay, now that K is a constant of nature. It doesn't depend on where you are, temperature, anything else. It's a constant of nature. And here's what it is. That K, Coulomb's law, is equal to, it's called Coulomb's constant, or the electrostatic constant, okay, is 9.00 times 10 to the 9th. Wow. 10 to the 9th Newton meter squared per Coulomb squared. Okay, 9, and let's see, we counted up to that before. 3 would be 1,000, 6 would be a million. This is 9 billion Newton meter squared per Coulomb squared. It's a pretty hefty constant. Okay, now notice why the units have to be that way. Newton is what we use to measure, come on pen, okay, Newton is what we use to measure the force, so this constant has to have a Newton in it, but it needs to have a meter squared to cancel out the meter squared down here. It has to have a per Coulomb squared to cancel out the Coulomb squared here. You always measure charges in coulombs, not in electron charges. Okay, now there is another example. Trying this activity, attracting water. You can do that if you want. Let's do the example at the bottom of page 456 using Coulomb's law. Okay, so I'm going to clear my slide, my white page here, and here it is. Two charges. So the two charges, we'll call it Q1 because that's what they called it. Each with the same magnitude. So Q1 and Q2 have the same magnitude, and that is, we're not going to mess with signs. We're not care whether they're positive or negative. They're 6.50 microcoulombs. Now I think you've run into that micro symbol before. That's millionth of a coulomb. Milli, a little m, would be thousandths of a coulomb. This is 6.50 millionths of a coulomb. So the other way that I would express that, and I think it's probably, yeah, quit doing that. Okay. Okay. This is so hard to write. I'm left-handed. I always wrap my fingers around and they hit a button here, and I can't get, there it is. Okay, finally I got it. So I would express this as 6 why won't it go? Okay, there it is. And it this drives me nuts. I have to write on that part of the board is equal to 6.50, and what micro means is times 10 to the minus 6. That means millionths of a coulomb. So that's the way I would write it, not microcoulomb, but 10 to the minus 6 coulomb. That's what micro means. Okay? Separated a distance of 0.200 centimeters. So that's what the book was calling the R. I called it D, but they call it R. 0. Come on, the pen just won't. There it goes. Okay, 0.200 centimeters. Well, again, they're using centimeters. Well, what's that? that's the same as 0.200 times 10 to the, a centimeter is a hundredth, so that would be minus 2 meters. Now, since you have a decimal here, you could move that decimal place one place to the right, making this a bigger number here, which means you make your exponent smaller, and since it's negative, we'll make it a 3. Okay, so you could write that as 2.00 times 10 to the negative 3 meters. Same thing. 0.2 centimeters is the same as 2 millimeters. 2 millimeters is 10 to the minus 3 meters. 2 times 10 to the minus 3 meters. Okay, so now we've got everything in the right units that we can use. Okay, and then let's remind ourselves what Coulomb's law is, that F, the force between them, that's what it's asking for. Find the force of repulsion between them. Now they say they each have magnitude of plus 6.50 microcoulombs. I said they weren't letting the signs matter, but they're now saying they are. So this is going to be a force of repulsion. They're pushing apart with a force, a pretty strong force, by the way. Well, Coulomb's law says this is K times Q1 times Q2 divided by R squared. Okay, remember that K was a pretty big number itself, 9.00 times 10 to the 9th Newton meter squared per Coulomb squared. That's supposed to be a 2, but it wouldn't write well. Okay, and that's multiplied by 6.5. Yuck! No. 6.50 times 10 to the minus 6 coulombs. You see, we need everything in coulombs so they'll cancel out. Microcoulombs would not be a good thing to have. Well, that's one of them. Multiply by the other one, also 6.50 times 10 to the minus 6 coulombs. Okay, and divide those two by 2.00, because I changed it to meters, times 10 to the minus 3 meters. We changed it to meters, but you've got to square that. So you square both the number and square the units. Okay, now I could do this kind of by hand in my head, but that would probably be hard to follow. Let's see if we can do it on the calculator. Okay. Alright. Now I'm going to turn my calculator sideways because I'm going to have to use scientific notation. So let's start with the 9, and you don't have to do the 0.00. Remember, to get scientific notation, you don't do times 10, you find your EE key or your EXP key, whichever that is, okay? Mine is EE, right there, the one that you see, okay? And that would be 9, okay, times 6.5, you don't have to put the 0 if you want to, EE. Now, since I'm using my phone, I have to type in the 6 and then change the sign of the 6, times another 6.5, EE, 6, change sign, and divide that by 2, you don't have to type in the 0.00, EE negative 3, so it would be 3 change sign, and I messed it up because you really need to put all that in parentheses. Okay, sorry. Let's clear that. Okay, clear that. Let's start over. Okay, sorry. 9 EE 9 times 6.5 EE 6 change sign times 6.5 EE 6 change sign divided by, now here's where I do parentheses, okay, 2, open parentheses, okay, 2 EE 3 change sign, close parentheses, and then the square key, x squared key right there, and then press equal. Wow, look at that force. Okay, that force is, if I did it right, 95,000, and there my third digit is a 0. Look to the right, it's a 6. That rounds up to a 1, 0, 0 newtons. Okay, let's see if the units are right. Meter squared, they canceled out. Coulomb squared, they cancel with coulombs times coulomb. So sure enough, that would be newtons. Let's see what they got in the book. 9.5, they put it in scientific notation. I left it like my calculator. You could write that as 9.51 times 10 to the, let's see, move your decimal 1, 2, 3, 4 places, so that's 10 to the 4th newtons. Now, for some reason, you just don't normally see it. You could have written that, though you don't usually see it done this way, as 95.1 kilonewtons. I don't know why, but you never see them express forces in kilonewtons. I don't see them anyway. They usually use scientific notation and put it in newtons. I don't know why. In fact, I don't even know if that's valid, but I've just seldom if ever seen it. I don't remember ever seeing it. Okay. Now, that finishes 17.3. Okay. Homework exercise in 17.3 would be any of the odds 1 through 7. Not too many of them there, but there they are. So let's move on to electric fields, 17.4. Now, again, it's not going to let me type. I don't know why. Okay? So I'll just read you the term. In terms of static electricity, an electric field exists where an electric force, like we just calculated here, and it could be, this was a repulsion because they were same signs. It could be attraction if they were opposite signs. Any electric force acts on a charge brought into that area. Okay? And they show the example of a charged balloon stuck to the wall here. What they did probably to charge it is rub it on their head if they had enough hair to rub. I hardly do. In the back I do. Rub it against their hair, giving it a charge. Stick it against the wall. It sticks because there's a force of attraction. Because rubbing against my head would knock electrons off my hair onto the balloon, so it's a negative charge. The wall is neutral. That's close enough to being opposite charges. It sticks. That means there's electric field around that balloon once I got it charged. Anytime you have a net charge, you have a field around it. Okay? Remember that. Now, the way we express that field is by drawing arrows to indicate the field. If you have a net positive charge here, the arrows are always pointing away from it. If you have a net negative charge here, the arrows are always pointing toward it, indicating that's the direction a positive, a tiny little test charge, positive test charge, will go to the negative, away from the positive. So that's how we define our field, and they represent it by arrows. Here is the formula that we use for electric fields, a pretty simple one. The electric field is related to the force, but divided by a small positive test charge. I'm sorry, I called it Q0. This text calls it, well, I can't do my eraser now either. It's just all screwed up. They call it Q prime. The charge on a small positive test charge. Okay? The force on a test charge placed in the field, and the Q prime is the amount of that test charge. So I'm going to clear that out of the way, and we'll do our first example. Example 1 on page 458. A positive test charge of 30.0 microcoulombs. So that's going to be our Q prime. That's the test charge. As soon as they said test charge, make that Q prime. And that's equal to 30.0 microcoulombs, which is a pretty small amount. But remember, I don't like, everything we do deals with coulombs, so get that in terms of 30.0. Micro means times 10 to the minus 6. Micro means a millionth, 10 to the minus 6 coulombs. Change that micro to times 10 to the minus 6. Now if you want to move the decimal, you could move it one more space to the left, making it a smaller number here, so you would increase this by 1, add 1 to minus 6, you get minus 5. I see no reason to do that, so we'll leave it like that. Okay? It's placed in an electric field. The force on it is 60, so the force on that charge by the electric field you put it in is given to be 0.600 newtons. Okay? The question is, what's the magnitude of electric field? That's what we're looking for. What is your electric field? We're not going to concern ourselves with the direction so much, just the magnitude. Okay? Of the electric field at that location of the test charge. Okay? Well, that's what we know. The formula we know is F divided by Q prime. So we just plug and chug. This is 0.600 newtons divided by, the Q is 30.0 times 10 to the minus 6 coulombs. Okay? Now, I'm sorry, the only thing I can figure is something like a pinched nerve in my hip, that when I sit too long, boy, it just aches. So I'm sort of wiggling around too much. Sorry about that. Just need to take the pressure off somehow here. Okay, get my calculator back active again. And that would be 0.6, you don't have to put the extra zeros, divided by 30, oh wait, turn it sideways. Okay, 30 EE6, change sign, equal. Oh goodness, that would be, on my calculator it reads 20,000, and the units for electric field, I need to get my Wacom tablet down here, The units for electric field are newtons per coulomb. That's about what we got. That's 20,000 newtons per coulomb. Okay, there is another unit you'll sometimes see for that, but we won't mess with that now. If you wanted that in scientific notation, that's 2.00. And by the way, 3 significant digits there, 3 there, so only that 0 is significant. I mean, the first 2 zeros are significant, okay? The last 2 are not. So 2.00 times 10. How many decimal places did you move it? 1, 2, 3, 4 times 10 to the 4th Newton per coulomb. Okay. Oh man. All right, this is not looking good for traveling 5 hours tomorrow if I can't sit. And what happens is it makes my knee ache. Something about that nerve that's getting pinched there just makes my knee ache like crazy. So basically I think I'm going to have to stand up and stretch out a bit. Sorry about that. Most of the time I can go a whole class without doing that, but today I've been sitting most of the day, either the first 2 classes, advising students, and whatever. Okay, so that's the answer they got in the book, 2.00 times 10 to the 4th newtons per coulomb. Now, electric fields are used in all kinds of places, especially electronics. Believe it or not, what you're doing if you watch television or a computer screen, you have an electric field firing things at the screen that react to the screen somehow reacts. This is only a black screen. Oh no, I could change color and it would be red then. A color TV has literally, how they do it is incredible, is sending all sorts of things. It's going so fast you don't see it. It looks like a continuous picture. What's happening? Fields are changing incrementally fast, you know, and just firing these things, you know, row after row after row after row after row, so it looks like a continuous picture firing at the screen, and the screen reacts in certain ways. So that's what they show here, your TV screen. And this is basically an old kind. The new plasma screens are even more incredible of how they do it. Now, for some reason here, they put in lightning safety, okay? And it is an important subject. I don't know if it's all that important to you in your course of study in diagnostic medical sonography. This is a rather bizarre looking, it's just sort of conceptual. That is one beautiful sunny looking day for someone to be worried about lightning safety. Okay, so I think they're just showing that. If I were that, I would get down in the bottom of that sand pit, not on the edge. But he's absolutely right not to get under those trees you see in the distance, to get down as low as possible, to create the lowest profile possible and be there. You don't run to the bushes. Get as low as you possibly can go. And the bottom of the sand pit or sand trap is where I would go. Well, that's it for 17.4. Okay, there's one example, but 4 exercises. Any of the odds 1 through 7. Okay, now let's start talking about simple circuits. Okay, that's the next section, 17.5. Okay, now there are 2 forms of circuits. One of these is called direct current circuits. The other is alternating current circuits. Now there are some fairly major differences between them, but pretty much all the laws apply to both. So we're not going to make a distinction in most of what we do. If we got over into chapter 18 or 19, we might make some distinctions. But even then, we generally don't. Okay? All the things we're going to do are going to be treated similarly. Here's the main difference. Okay, we just mentioned in the previous section, 17.4, electric fields. Really, the electric fields are doing all the work. They're the things doing the work. They're the force per unit charge, okay? You think that the charges are doing the work. No, they're not. They really aren't. They're just the devices that are carrying the energy, basically, okay? But they're not really doing the heavy lifting, okay? Now, in a direct current, all the charges tend to move in one direction. That's why they call it direct current. In an alternating current, the charges are constantly changing direction. I mean, 60 changes of directions every second. So I can't even move my finger fast enough to indicate that. So the charges really aren't going anywhere. They're just going back and forth, back and forth, back and forth. But it's the energy that they're having, that's what's doing the work. That's what's carrying the burden. So it really doesn't matter whether it's a direct current where the charges are moving. And by the way, they don't move very fast either. They move incredibly slowly. The field sets up almost instantaneously, almost at the speed of light. Okay? The field is what matters, not the actual motion of the charges. So it really doesn't matter most of the time between alternating currents and direct currents. There are some places where it would matter. I don't think you'll be concerned with those. Now here's how we represent a circuit, or a very simple circuit. Okay? That is a flashlight, battery powered flashlight. You see up at the top that two parallel lines, one big, one small, that represents a battery basically, but you can use it to represent a power supply. That's where the charge gets its energy. Okay, down at the bottom they drew sort of a light bulb looking thing. That's where the energy gets used in the flashlight. There is a switch there. If the switch is open, there is no circuit at all. It's there, but if the switch is open, the charges do not move, and that's why the light doesn't come on. But as soon as you close the switch, that doesn't mean the charges get flying from the battery to the bulb. No. The field is established. The electric field, the E, is established immediately, almost immediately. Almost the speed of light, the field is established. And the charges start moving. But you see, there's always charges in the wire, or in the circuit there, and as soon as the field hits, all the charges move. The ones right near the light, the ones right near the battery, and everyone in between, they start moving. Now that truly is a battery, so they're moving one direction, and that's direct current. Okay. The source of energy is not the charge. The source of energy is the object that supplies the electrical energy for the flow of the electric charges in the circuit. Okay? Now that in this battery, in that flashlight, was a battery. That's a chemical cell that is a direct, sets up a direct current, makes the charges move in one direction. The charges are not what's doing the work. It's the energy that that battery gives those charges. Okay? Now, here is sort of a diagram. This isn't in your PowerPoint, and I can't really draw that myself, but there's sort of the diagram I don't see where the battery is in that. Oh yeah, up at the top. There's the battery. That gives the energy to the charges. And they take off and go to the first load, and first load may use some of that energy. Some of it goes on to the second load. The second load uses the rest of it. The same charges that leave the battery, they come back to the battery. You don't use up charge, you use the energy that the charges carry. You can't create or destroy charges, you use the energy that they carry. Okay. Now, again, a battery is two different materials that have, they call them different electronegativity, and that's what creates the energy. Now, we finally go back, I only got 5 minutes, so let's see if we can get this done, to finally hitting the next PowerPoint here. Okay, now this represents the battery. There's a chemical reaction here that moves some charges up and some charges down. The way they've oriented this one shows that the electrons are moved up and the positive charges are moved down. They're not strictly protons. You don't ever move protons. What you move are ions. Positively charged ions move this way, negatively charged ions move that way. That gives a negative charge on this pole of the battery, a positive charge on this pole. Okay? Now, if you were really concerned with electrons moving, that's what moves is electrons. They flow from negative to positive. Now, I don't know if it's Benjamin Franklin's fault, but if he'd only named them the other way, then it would fit everything in physics. Because usually we say that things travel from high potential to low potential. So therefore, we often talk about the conventional charge. That would be, if you had positive charges, they would move this way. Electrons being negative charges, they move in the opposite direction. It doesn't matter. All that matters is the electrons are carrying the energy. The energy is delivered to the load. The load uses the energy. Those same electrons make their way back to the battery to get more energy. That's what's happening in an electric circuit. Now they liken it to a pump. I don't know if you realize it, but this is what happens. Anytime you see a water tower there, what happens is they've got an electric motor somewhere down there is pumping the water up into the tower, always keeping the tower probably pretty close to full of water. You probably have a thing up there, and when the water goes below a certain level, it closes the switch, turns on the pump, and it moves the water up here. Okay? That's like the battery. It's moving the water from a low potential, low energy level to a higher energy level. Then from the tower, everybody's water is connected there. Everybody is downhill from the tower, so the water flows by gravity to everybody's home. Okay? But they're showing a short circuit of that. The tower is providing water to turn a turbine. The turbine is then turns like this. That's using the energy that the water had by being pumped up here, and now that water goes back here. So in this analogy, the water is like the charges. It's not the water necessarily that's turning the turbine, it's the energy that the water has. You could dip the turbine into water and it wouldn't turn. So it's not water doing it, it's the energy of the water that turns the turbine. So it's not the electrons flowing through here that lights the bulb, it's the energy that the electrons are carrying. That's what lights the bulb. Where do they get the energy? From the battery, which moves ions one way, negative ions one way, positive ions the other way, setting up, and we're going to get to this later, a potential difference. Okay? So that's your water pump analogy that they use all the time in uh, electricity, making an analogy. We've got 1 minute. Let's see if we can hit just a couple more definitions. The wire here that they represent here is called the conductor. That's the thing that carries the charge. The charge has energy, loses energy, but the charge has to come back. If you have an opening in the wire, no charges move. Now, if you have a burst pipe, the water flows out. That's where this analogy falls apart. You don't have electrons spilling onto the carpet here. They just quit moving. If there's a break in the circuit, there's no more movement. Okay? So there's one difference in that analogy. Okay, I think we just ran out of time. So what I'm going to do is next time we'll start with insulators and conductors. Okay, so we'll start there next time. I don't think we got enough, we didn't get any formulas yet in this section, so we'll stop there and pick up in 17.5. Then we'll go to Ohm's Law. That's a fairly short section. Then we'll do 17.7. 17.6 is Ohm's Law, 17.7 is simple circuits, and 17.8 is parallel circuits. I think I got that wrong. 17.7 is series circuits. I misread it. 17.8 is parallel circuits. And if we can get there, we'll do, oh yeah, I'm sure we will. We will get to compound circuits. Okay, we may actually finish 17. If not next time, we'll finish it on Thursday. We may get a little bit into 18. We're not going to do the later sections here. We get a little bit into 18 just so you'll get a little taste of magnetism, but I probably won't test you on it. I'll probably just test you on 17 next week. Okay? Any questions? All right. Good deal. I hope you have a good weekend. You four here that are in class, you pretty much up to date. You don't have a turn-in test 4, but I just gave it to you on Tuesday. We just finished the chapter today. So get that to me. If you can't get it to me by Tuesday, get it to me by Thursday. That'll be fine. Okay? However, the test on chapter 17 that I'll give you on Thursday, you only have Friday, Saturday, and Sunday to work on it. The sooner you can get it to me, the better. Please don't turn it in on Monday morning. I mean, don't fail to turn it in. Get it to me. If you don't get it to me until Monday morning, the odds are I have to give you an incomplete until I can get it graded and then change the incomplete to a grade. It won't take long, but there's just no way I can grade a bunch of papers on Monday morning and get all the grades in Blackboard and get the averages done and everything out there. I'm going to have to call it quits on grading Monday morning and just start assigning grades. Okay? So try to get it. The test 4 that I gave you last time, try to get that to me either Tuesday or Thursday. And then test 5, which I'll give you on Thursday, try to get it to me Friday, Saturday, or Sunday. Okay? Any questions? All right. All right. I was going to say I must have put you all to sleep. Okay. So I'm going to stop sharing. I'm tired of sharing. And unless somebody has a question, I'll end the meeting. Any questions? I guess not. People are leaving. Take care. Have a good weekend. We'll see you Tuesday. Bye-bye.